Okay, who recognizes that? Yeah, that is the beginning of our recent, like the past 15 years or so, YouTube videos of Saturday Morning Physics. Good morning. And welcome everybody. Hi everyone here on the University of Michigan campus, and hello to those who are joining us online for welcome to a special Saturday Morning Physics. They're all special. This one is particularly special because we are celebrating 30 years of Saturday Morning Physics. And our appreciative and wonderful Saturday Morning Physics fans over this time. I see a few people here who might be younger than 30, but that's the idea, because this is also one of our family-friendly Saturday Morning Physics presentations, shows, and so on. And I know many people have already enjoyed and experienced the demos, which we'll talk much more about today, and which is really what today is about, in the gallery outside, and you'll have a chance to do that as well after this show. So I'm Physics Professor Tim Chupp. I'm one of the organizers of Saturday Morning Physics, along with Professor Christine Aidala, Carol Raybuck, who's been the stalwart glue and organizer of this, and Monica Wood. We formed the committee. I'll say more about Monica in a moment. So before moving on to our presentation, I want to remind you that Saturday Morning Physics is made possible by you, by your many generous contributions, by your attendance, and by the word that you get out about Saturday Morning Physics. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Pulakeshi Dayalu Astrophysics Fund, and the Van Loo Family Endowment. And if you would like to learn more about giving and supporting Saturday Morning Physics, please go to saturdaymorningphysics.org. Before moving on, we have not written, but we will now write an email address that those online, or even those here, can send questions to if you have them. We'll have a very brief question and answer period at the end of the show, but not as long as usual because we want to move on to having you enjoy the demos. So let's see. Saturday Morning Physics is 30 years old. So that, if you do the math, was 1995. And I don't have any equations here, but that works. Anyway, it was physics professor Dan Amadei, who's right here in the room, who had this idea. We really need to acknowledge Dan's contribution. Who had this idea. He was a younger assistant professor at the time, and he came here from Fermilab, where he did his postdoctoral research. And Fermilab had a program called Saturday Morning Physics, still does. It was started by Leon Lederman, who was a remarkable leader of Fermilab, educator, humorist, and author of a book called The God Particle, a very modest person as well. And this was originally modeled on the Fermilab program, which was designed to have postdocs, I wasn't going to show this yet, postdocs give talks to get experience and also to engage with the public. This is public engagement. Now, 1995, I just thought the other thing about this was the idea was to give people an alternative to tailgating on football Saturdays. So we call it physics tailgating. And I did go back and look at the 1995, 30-year ago football season, which is here. So just very, very briefly, you might recognize the record, 9-3. You might recognize the second to the last line, which didn't happen this year. And this was Lloyd Carr's first year, so one of the great coaches in my tenure here at the University of Michigan. And the bowl game didn't work out so well either. Anyway, the first lecture was given by Dr. Robert Welsh. He was actually a postdoc in my group, so that's my initial connection in supporting this. And it was quite remarkable in many ways. First of all, this doesn't look like a physics talk, right? This is medical imaging, and the animal on the left, that's an animal, is a rat. So, but Robert explained this very well, and Robert is now a professor of radiology in the University of North Dakota, I believe. So this was what the first series of 3 lectures was about. One interesting thing about this was that this is the room that Dan found to give this. This room is still a classroom. It holds 40 people. And there were 40 people seated and about 60 or 80 people outside in the hallway. So the lecture was delayed for about 20 minutes while we came to this room, and we've been here ever since. So that's how Saturday Morning Physics started. That's me. A few years later, we started with, Dan.
That was a deliberate contingency plan.
There was.
That was we were unsure how many people would show up.
Yeah.
So we had a plan to move here in the bizarre event that we got more than 40 people.
So Dan corrects me, for those who didn't hear, and he was much better than I gave him credit for because he had actually planned for an overflow crowd. They didn't know how popular it would be, but it's been incredibly popular. So we've pretty much filled this room every Saturday morning with a Saturday Morning Physics since until the pandemic, which made some changes. But it's pretty much full today, so welcome everybody. I just wanted to note that there have been a number of changes. One is that there was a spring series, and the decision was to have faculty do it, so I don't know if I did the first one, but it was one of the first. It was 3, and so they tended to be a series of 3 lectures. Now we often have single lectures. This is a very incomplete list, and I'm going to apologize to people who are here, but Dan, Myron Campbell, who told me he couldn't be here today, Fred Adams, Roy Clark was intended to be here. Roy has been my partner in organizing this at least since before the start of the pandemic. And one of the things that we recognized in the pandemic, of course, everybody stopped in the spring of 2020, the winter of 2020, so we canceled a few events. But we started right up again in the fall in an empty room, taping lectures and then broadcasting them and having a live question and answer. And that goes on to this day. So our live broadcast resulted from the pandemic, and we all adjusted. Gus Everard, Vanessa C., Rachel Goldman, and Christine Idala, and others. So the faculty who've organized this have found speakers, found new ways to make Saturday Morning Physics very special. So we're 30, and a lot has changed. There was a brief interlude of bagels, but we realized that donuts are the thing. So I'd say that donuts and demos is one of the things that characterizes Saturday Morning Physics. So I just have another minute to, they allowed me to do a demo. And it's a demo. We tell you, what we do. Demos are used for teaching physics, and this is heavy, which is a concern. So here's the idea. This thing swings, back and forth. And there's a concept in physics that we like to teach early on called conservation of energy, which is a very broad idea, but this is what's called mechanical energy. or moving energy, but also gravitational energy, which is sometimes called potential energy. And you might not be surprised that the ball, when released the first time, never comes back further, at least, than it was released from. And it's always a little bit less, because there's another way. There's a way that energy is lost. So this is what people are supposed to do to show how much faith we have in the laws of physics, is to do this, to let it go. And the thing is, that there's also sources that can add energy. Think about it. The door's open. Maybe we should close it. Because if a wind were to blow, all right. But anyway, I'll do this, and then we'll move on. Okay. So just to see. Now, oftentimes, I'm not going to take any more time for myself, but oftentimes there's a whole number of reasons to pause. So let's see. These demos, where did I do with that? Thanks. Demos and donuts. This is why, and it's the why for a lot of things. So was that engaging? I'd say you get your attention, right, with the demos. Sometimes they're exciting, at least it was for me, I promise. Entertaining, depends on who does it, and educational. So this is an equation, it's, but it relates the energy before I release the ball to the energy after I release the ball on the left and right-hand sides. So we do all these demos. Where do they come from? Well, actually, they come from a room that's below your seats here. And do we have a picture of that? Okay, that's great. So it looks like this. It's filled with shelves and demos, and they pull them out all the time. Okay, so all I want to do now is introduce the team, Sean Riley, and they're busy, all right? He's the newest member of the demo lab. Nick Arnold is busy. He'll be here. And Monica Wood, who started at the demo lab in 2010 and has led it since 2016. She's amazing. She does this and many, many other things. So I'd really like to spend a lot of time saying how great they all are, but I want to turn it over to them. So Monica.
Well, thank you very much, Tim. Welcome, everybody. We're here to celebrate, right? So let's get into it, because 30 years is a lot of information to get through. So again, the main reason we're here is really to show the everyday impact of science. You see it everywhere you go. We're going to see many examples of it today, and those online wouldn't be able to watch it if we didn't have it. And so I wanted to start out with a question. I'm not sure how many of you got to see this survey ahead of time, but if you want to submit your answers now, I'll go ahead and let you. But the main thing that I wanted to ask is, how many times have you been here before? And so I'm going to switch it over in about a moment. I see some phones getting out, and those online, please feel free to participate. I love all the participation. All right. And so I'm going to go ahead and move it forward. The QR code will move to the left of the screen. And so now we can have a little breakdown of who is here, based on percentages, of course. And so it should be updating live, which is really neat. It looks like none of our only online fans have joined in, but you can see that we have quite a few first-timers. So welcome, welcome. We're really happy to have you a part of the SMP family. And we got a good breakdown between occasional and longtime patrons. And so for all you longtime people, hope you enjoy the nice travel through history that we have here for today. All right, so feel free to continue entering. We would love to capture this data after the talk. But let's move on, shall we? All right, so the real question is, how do we do this? Well, Tim alluded that we have a committee of people that are tasked with trying to find cutting-edge topics. And so what kind of cutting-edge topics could we talk about in a Saturday morning physics? Well, we could start with physics, right? Physics covers a whole lot of stuff. We've got the largest structures in our universe. We can determine, or we can explore how it all began, and in the end, what our fate is. So that would be cosmology. We could study the tiny, and we can look at what the origins of matter are, and possibly some of the substructure within that tiny stuff. We could go to other worlds and see how that's different than our own. Oh, and we could talk about the Nobel Prizes that have been won over the years. And so the first one that's worth mentioning is Madame Curie, of course. She is one of the few people that have ever won more than one Nobel Prize. And her work was actually featured in a 3-part series in 2000. To go on more recent, we had a Nobel Prize talk about the 2011 Nobel Prize for Cosmological Expansion, and we had a talk from Dragan Huder who talked about the importance of this discovery. We had the Nobel Prize discussion of the 2013 Higgs boson. We had a couple regarding this. What was great about this discovery is that the ATLAS project, which is the experimental confirmation of this theory, has a very strong Michigan roots, and so it was really nice to have Bing Zhao and James Wells come and talk about that important discovery. We had the Nobel Prize in 2018 for chirp pulse amplification, and so this was primarily focused in the light fantastic from Thomas, there we go. But we also had a couple graduate students talk about their work and their role within the application of this discovery. And then one of the ones that was so interesting for me was gravitational waves. And so this got the Nobel Prize in 2017. But what was neat about this is that we had a talk by Keith Riles, a couple of talks by Keith Riles, who was part of the experimentation group that actually helped and discover this effect. And what their group did was they had recorded this chirp, which is as these two these two large bodies came closer, they got closer and closer until they collided, essentially, or combined, and we could essentially take the signal that was recorded from the LIGO experiment and ramp it up to auditory frequencies and hear the result. The first one's a little quiet. Oh. And so that was a 400 hertz frequency shift for the actual data that they recorded. But the neatest thing was they asked us to build a demo to replicate that, and we did. And so I would like a volunteer. Come on. All right. And so what we have here is an anvil, which is just a really hardened steel, and then a ball bearing, which is also hardened steel. And what happens is every time ball bounces, it loses just a little bit of energy. But as it gets closer and closer to nothing, you'll start to hear the frequency change of the bouncing. And so I want you guys to pay attention to that. So when you're ready, go ahead and bounce that in the tube. Oh, and thank you very much. And what was your name? What was your name? Jack. Everybody, let's thank Jack for his help today. So again, the other thing that was funny about this was that we built this for Keith, and Keith came and tried it, and he went to demonstrate it, and he started to go like this before the actual climb up, and so it was actually a little silly in the end. But that one was a memorable one for me. Now, the other thing that we do is we could then take it beyond physics and actually apply it to the other things around us, right? Whether we do it through engineering, whether it's advanced materials, engineering or energy solutions, medical imaging, genetics, or sports, of course. We can't talk about physics without sports. But the other thing that we can do is really improve scientific communication. And we can do this a number of ways. We could either do this through art, through history, or even through science policy. And so that is another aspect of our program that we try to bring to the general public, is to give this context so that you can make informed decisions. So Tim would like to say, maybe we're not just Saturday physics, we're just Saturday not just physics. But then Carol's like, I think I have one better. We're Saturday morning, everything is physics. And so, thank you for that, Carol. So I'll leave it to you on which one you prefer, but either way, it is important to know that physics is in everything. Now, the other challenge of figuring out what topics to talk about is then to find expert speakers to do the talking, right? And so again, this committee that we have formed, and over the years it was primarily in the faculty's responsibilities, we had to search for speakers. The easy, low-hanging fruit is our own backyard, whether it's physics faculty from around the university, postdocs, researchers, or staff members like us, demo labbers, as well as graduate students, and giving them the opportunity to get their presentation skills developed as well. But not only do we do our own backyard, we go beyond. We look for people from other institutions like MIT, Johns Hopkins, and other places. And I just want to note our most watched SMP video is Sean Carroll, who was a visiting faculty member from Johns Hopkins, who talked about quantum, and I highly recommend to check it out on your free time. Another thing that we try to, the other type of people we try to invite are national and international experts. So this could be from Fermilab, Rydberg Technologies, and of course NASA. And so Tim alluded this a little bit in his introduction, but one of the most exciting and complicated SMPs we put together was when we got to connect with the astronaut on the International Space Station. So this is Josh Cassada, and he asked us if we would do this, and poor Carol had 15 days over the holidays to prepare this lecture for over 600 people, with the help, of course, of IT and other people around the department, or around the university, but we were successful in making this happen. And one of the neatest things that came out of this was a video of a demonstration live from the International Space Station. And so I think I've been having trouble with the beginning of my sound starting, so if you don't hear it, that is Nicole. She's a fighter pilot.
Right now, this morning.
I'll leave it for her to continue.
So if you try to drill something in space, you're actually going to try to spin the other way unless you find a way to lock yourself down. So let me show you one thing that Nicole and I have been messing around with.
Well, thank you again, Josh. Yes. So all of us have likely enjoyed that, but if you were Tim Chupp, you saw a physics problem out of it. And so he spent some time on how you would actually solve this, not based on Earth, but up in the International Space Station. So if you're curious and want to know a nice applicable physics problem, go see him after the lecture. He also has a demo that will help give you some context. But this event was almost entirely eclipsed by our very own astronaut Vivian. She was a 5-year-old girl who asked the first question to Josh, and it was astronaut Vivian's show. All right, so the other neat aspect of speakers we've had here have been the authors, the artists, the linguists, and other people who help improve communication across genres. And so some of the notable ones are Jim Adiavani. His talk was very inspiring to me because he talked about the importance of pictures and concise words to actually get your point across, but the picture is more important than anything. Coming from a comic artist, of course. We also had Jorge and Daniel come from, Jorge's from the PhD Comics. One thing that was really neat about their talk is Jorge had animated live in the middle of the talk, and so I'll let them take it from here. And sorry.
Learn about the Age of Explorers. You also sort of feel like maybe it's over, right? Like there aren't any more continents to discover. There aren't any more islands to land on and name after yourself, right? Most of the fruits have been tasted, probably. So that's a little bit of a come down. And then the more you look around at the world, the more you marvel at our technological achievements, right? I mean, we have airplanes that can fly across oceans. You can download all of human knowledge onto a tiny device you fit into your pocket, right? Clearly, we live in an age of wonders, right? And you might be forgiven for thinking science has it mostly figured out. You know, we've mapped out the world, we've mastered technology, and physics has mostly figured everything out. It's just a couple of details left, right? Which means Brad Pitt has no excuse not to call me, right? Wherever he is, he could pick up the phone.
And so the most important person from this category I like to feature is our very own former dean and radio superstar, Ann Curzan. And she just had a talk earlier this semester that is worth checking out, the language of science, and so I highly recommend it. All right, so 30 years of information is a lot to go through. I decided to ask AI for help, and they prompted, without asking, to provide me a description of the speaker composition of Saturday Physics, and I couldn't help but share it with you guys. So it says, the composition of speakers is like a complex crystal lattice structure. The physics department forms the dense repeating core, or the primary unit, consistently providing the backbone of the program. Surrounding this core are specific integrated components, the engineering, chemistry, and astronomy departments, which represent highly defined, closely related units. Then, the graduate students and the research fellows are the crucial interstitial sites, consistently bringing fresh, cutting-edge results and energy to the entire structure. Finally, the external speakers are like specialized dope agents, introducing exotic materials or ideas from distant sources to alter and enhance the properties of the whole system. So I couldn't help it. I just thought that was way too elegant to not share with all of you. All right, so I have another question for you. I wanted to ask, have you guys watched us online? And if you haven't, our YouTube channel is part of the Michigan channel. We have a SMP playlist. But let's go ahead and see. Oh, quite a lot of you. Oh, wait, hold on. It didn't. Go forward. Here we go. Oh, got to pop out. Oh, no. What you doing here? All right. We're just going to skip it. If we have time, we'll come back, but I'm not going to waste time on that. But the point is our media production has changed over the years. And so it began, as Tim had talked about, in this room. It started out as faculty lectures. It began to be recorded by the demo staff, which I think was in 2000, but Mark could maybe correct me if I was wrong. But then it moved into professional recording through Michigan Productions. They began in 2002. They would take our recordings, they would edit it for public broadcast television, and give Carol a DVD of the recording. So this was before the internet and all of the beauty of YouTube. We were also a test bed for a system called Karma. And so back in 2006, Homer Neal, who was a former department chair and APS, American Fiscal Society president, and his colleagues at the Atlas Project, they needed a way to do lecture capture and provide it to all of the people around the world who worked on the project. They ended up developing a device that the microphone would be tracked by the camera and help to make sure the person who's talking is always being captured. We were the test bed for this, and it ended up being purchased and moved over to the engineering college in 2013 until it was killed by Zoom and the pandemic. But that's okay. We're all better for it now, right? But of course, that was also the birth of YouTube when it moved to the engineering college. And so again, there is our YouTube channel if you have not checked it out. And then, of course, COVID hit. We had to shut down everything. We didn't get to finish our season that year, but we did come back. It was important to come back because we did not want to be one of the casualties of such a horrible time in all of our lives. But we didn't want to lose the in-room feel. So we ended up still recording in person to an empty lecture hall, but those who watched online, you're experiencing this in the same way that we had back when the pandemic hit. Then, of course, the International Space Station. We had such an amazing event there. It took us outside of this room, and it couldn't have gone on better. And really, a lot of people did a lot of work in a short amount of time to make that happen. And then today, we have taken the best of all of these avenues and offer it to you so that you can access it no matter where you are in the world. All right, so just to give you some numbers, and then we'll get into the fun. We've been around for 30 years. We've had 55 seasons, 418 lectures, over 375 unique speakers, and over 285 videos and counting. But of course, the most important, thousands of attendees. And so we thank you every time, every day for your attention. All right, so the fun. Thank you for waiting. So our job is really to make the invisible visible. We try to give you aspects to grasp all of these really complex and complicated topics. And so first, I should mention our team. That was, Tim gave us a good introduction. Sean, myself, and Nick, we are the current 3 staff members that service 30 different classes and multiple sections of each of those classes. We have over 1,000 demonstrations that professors from all over the university can use. And we don't just buy what we use. We build many of the things because, we got to make it so that Pasco can come take it and sell it to everybody else. And so the product of the pandemic was we also filmed all of our demonstrations. And so we have a separate YouTube page that is literally just us performing the demonstrations. And what's so exciting about this is that since the pandemic, our demonstrations have been used in classrooms around the world to help supplement their instruction as well. So, thank you guys. All right, so now here we go. Scientists observe the world around them, but they're not the only ones that can. We have plenty of senses on our own body to help us understand the world around us. So let's go ahead and start with our ears. So how many of you have dropped a rock into water and watched the ripples on the surface of the water? And so this is a wave propagating from that point of disturbance. So water waves, although the mechanisms are slightly different, sound will propagate through a room in a very similar fashion. And so if I had a single speaker at that 0 on the bottom axis, and I just play a tone, you will hear just the specific frequency. I think it's 2,500 hertz or something like that, around. And so nothing special, it fills the room. But if I then take 2 and separate them by a little distance and do the same thing, now you will get to hear a wave phenomenon known as wave interference. So go ahead and close one ear and move left, right, up, down, forward, back, but slowly. You should hear really loud spots and some really quiet spots. Were all of you able to hear that? Good. I'm not sure if the online can hear it, so hopefully you guys were able to indeed see these spots where the lines that are radiating from there, those are the dark spots. Those are the ones that the waves come in and they cancel each other out. And then the other parts are extra loud because that's where they're adding together. But we can do better. Let's go ahead and send this sound into a tube, okay? The sound energy will travel into the tube, bounce off the other side, and come back, and it's going to interfere. And we've heard that already, right? What if we could see it? All right? Oh, and Sean will be performing it for us. We need more power. There it goes. Yeah. And so what you're seeing is places where the flame is very high, that is where the pressure is the largest, and you get the most flame. And in the areas where there's almost nothing, you got the least amount of pressure, and so there's no gas there to push the flame. And as he changes that frequency, the pattern inside changes. And these are what are known as standing waves. And this is exactly what happens inside of instruments, and we've had a number of Saturday Physics on the physics of music, and so I highly recommend you going to check those out, including some from our faculty cohort, Christine Idala. So another sensor that we have, it's a very powerful sensor, is our eyeballs. Our eyes are able to pick up a lot of information. We can pick up intensity, how bright something is. We can pick up color. So we can tell, okay, this is kind of orangish, this is black, you know, my hair is a little red. But another thing that you can pick up with your eyes is temperature. So it turns out lights radiate at a given temperature based on the color that comes to your eye. And this is exactly what astronomers do when they look at stars to see what kind of gases might be in that star. They can determine some of that based on this temperature. And so over here I have a light. I'm going to go ahead and turn it on. Hopefully you guys can see it. It's a little orangish, right? Almost an orange-red. I know the lights are a little bright. Can you guys see that? Okay. Now I'm going to turn it up so it's going to get brighter, but I want you guys to pay attention to the color. So now it looks a little more yellow, right? Keep going. More yellow, and it might hurt, but you should see it start to get a little white. Okay, so I'm going to go ahead and turn that off. And so anybody who's built, oh, that's interesting, put together their own lighting in their house, they may have heard about the temperatures of light. And so your eye is able to see the total light coming from this lamp. But for those of you who may not know, if you send light through an object known as a prism, we are actually able to break up this light into its constituents, into all the little colors that are inside that light. And so we can see that white light is actually made up of reds, greens, blues, you know, the rainbow. And so this is where you get, this is one of the mechanisms that we are able to see the rainbow. And so if you look on the screen in the center, you'll see off to the right, there is a nice rainbow of the color as it travels through a device to help separate those lights. But your eyes can't really see that, right? Well, scientists have built a machine, or a tool, a sensor, and it's called a spectrometer. This allows them to actually see how much of each one of those colors make up the color that the full color that you see with your own eyes. And so in the center here, I have a graph of the intensity, which is how bright the light is, over wavelength, left and right. And so you've got really short wavelengths on this side. That is, you know, blues, green, or blues and purples. And then over here you have longer wavelengths, which are reds and oranges. And so when we have a light on at a low setting, you will see that the maximum, so yeah, go down to like 20. Okay. This one. So this shows you we've got a nice range of frequencies. Go ahead and hit it again. And we can see that the relative maximum of this is somewhere in this range, and so we'll just say right about here. And if you look at the light, it's kind of orangish, right? And so that maximum color is looking at about 692, which is not too far from red. If you then ramp up the light, we are now increasing the energy. We are seeing the position of the peak actually shift to a shorter wavelength. And so your eye is going to perceive this more yellow or even white, which in astronomy, there's a whole thing on that. But you can see now that that shift has happened just in this little bit of energy increase that we have provided. And so scientists use sensors to go beyond our own senses to really further understand the world around you. All right. So, like I said, our eyes are really good, but our eyes are only so good. We can see the reds to the purples, but there's stuff beyond that. We've got infrared, which is longer wavelengths. We've got ultraviolet, which are shorter wavelengths. But if you really, as good as our detectors are, it's really only pales into comparison of all of the things that we have to discover. So how are we going to do that? Well, we can use different sensors, right? We could have sensors that measure magnetism. And so magnetism is helpful. We see it in a lot of the technology around us today. But if you were to look at this on the table, it would just be that north-south bar. The black lines are invisible. You can't see magnetic fields. But if we get a sensor, this can actually pick up magnetic fields. So I have this board over here. It is hiding some things, but if I were to take this sensor, I can see, are there any magnetic fields present? No, no, no. Oh, so there must be a magnet right here. And this is even smart enough to tell me if it's north or south. If I go behind the wall and you guys can't see it, because no, you can't see it, I will get south on the other side. I guess I can't change it because I don't want to move it. But these types of things are very important to learn, not only to take advantage of it for technology, but also because it protects us from our important neighbor of the sun and all of the radiation that comes at us. And so without our magnetic field and understanding how it works, we could be in some danger. Another thing that what is often important for us to keep a track of is our presence of radioactivity. We need to know how safe do we really need to be around things, particularly if you're going to the doctor and you have to get a bunch of procedures done. You might have some radioactive material enter your body, and are you going to have to go and have this, big suit, big protective gear? No, because safety is recognized and monitored. But we could have a device called a Geiger counter, and this picks up radioactive decay. And not yet. We have stuff raining down on us at all times. Not much, especially when we're inside. But this is just our background radiation. This is coming from space. But if we put it close to something that is radioactive, it increases, showing us that maybe we should take a little bit more care around this part of the room. All right? And so another thing that we can actually do is build sensors that can see, again, beyond that visible spectrum. And one of the ones that we have is our infrared camera. And so this is good enough to maybe uncover something that is hiding behind the wall. Slowly appearing. I couldn't imagine what it is. And I'll get out of the way. Actually, I think that contrast helped. And so now you can see the invisible. You can't see the M from the outside, but that sensor is able to see through the cold wall and into the heat that is produced by a coil of wire in the shape of an M let's go this way, on the back. So there's the M, there's the magnet, and there's the radioactive material. But it also allows us to do additional energy accounting. Did you guys know that you radiate in the infrared? Say hello, everybody! All right. And so one thing I will notice, or hope you notice, is there's people wearing glasses. Your glasses actually block infrared. Glass will not allow infrared radiation to pass through it, and so your eyes look cold when you're wearing glasses versus the rest of your body that is full of heat. All right. So thank you for joining in. Again, these sensors, as well as our own senses, allow us to keep track of all the types of energy that are around us, because not everything is visible to our own self without it. And from a famous individual, I don't remember his name, but he helped, along with the development of the first law of thermodynamics, I believe, where energy is conserved. And so by being able to find and keep track of all of these sources of energy, we can then use this to probe environments that we can't readily go to. And so one talk that we had was all about planet formation. And they talked about the accretion disk. So those of you who were in the gallery hopefully got to play with our accretion disk. But we also feature it many times in our lecture. And so one of the things that happens with accretion disk is you've got a lot of gas and dust moving around. And when things move around, it gets hot, right? And so, if you were to rub your hands together, you start to feel your hands are getting warm, right? Well, the same thing happens in these kinds of environments. And so I have a demonstration here. It's just a wheel. I'm going to let it start spinning. I'm going to take a piece of wood, and I'm going to put some pressure on the back of this wheel. And you're going to look and see that I'm not lying, that when you rub your hands together, it gets hot as soon as it comes up. All right, here we go. All right, you can even smell the wood if you're up close. And I also mentioned magnetic fields are important. Well, there's a thing called eddy current braking, where you get to make something slow down using magnetic fields. So I'm not going to actually touch this disc. This is exactly how roller coasters work, with a lot of the newer roller coasters and their braking. And you see all of that energy doesn't get destroyed, it just transforms. And so with having extra sensors, we're able to actually account for that energy to help explain what might be happening in these extreme environments. Another place that we see this, it was discussed, I actually forgot to write down which lecture this came from, but we had somebody talking about black holes, and how do you wrap your head around the amount of energy that is in something as massive as this object? Well, we can't see what's inside of it, but we can see what's flying out of it, out of these jets, for instance. Well, if we use the idea of energy accounting, and if we have an idea of what might have started with, and we subtract what we can see, we can at least get an order of magnitude of what we might be missing. Sure, physics in these extreme environments may flex, but we could still get an idea. And so one of the professors actually used the idea of a cannon. And so if we have an object that starts together, a cannon and a ball, and we allow it to go, it takes a moment because what we're doing now is storing a bunch of energy inside of a capacitor, which is inside the box. We are then going to release all that energy at once through a piece of wire. It's going to vaporize, heat up the air behind the ball, and propel the ball. And this is going to be loud, so those of you in the room are going to probably want to cover your ears. And Nick will give you a countdown. 3, 2, 1. Very nice, very nice. So, thank you, Nick. So we saw the ball fly across the room. We would be able to measure that if we, did some measurements and calculated some things. But the other thing to notice is that the cannon moved backwards. So this would be the missing energy that we would be trying to determine based on what we could see happen in the visible world. Now I'm going to need one more volunteer. Come on. All right, and your name? What's your name? Charlotte. Everybody, let's have a round of applause for Charlotte. All right, so all I'm going to need you to do is you're going to put these on, and you can wait a second. And then when we give you the okay, you're going to do 3, 2, 1, and then you're just going to pull the pink cord, okay? Now, what we're going to do differently, and so let Nick tell you when you're ready. One thing that we're going to do differently this time is instead of it just being the amount of energy we charge and we release it, we're going to put something extra inside of the cannon. And that little bit of extra is going to maybe provide a little oomph. And hopefully we will see that if you start with a little bit more energy, you just might end with a little bit more energy. All right, so again, this is going to take a moment as we fill the capacitor full of energy. We've placed the cannon back where it started. The only thing we did differently is just add a little bit extra. And this is maybe a little louder too. All right. All right, in 3, 2, 1, go! Oh, good catch, good catch. All right. So clearly the ball went higher, faster, harder, right? So we must have started with more than what we did the first time. And so that's kind of how scientists will use these kinds of analogies to give them just a sense of the world that they're trying to explore. So now that we have sensors, let's look at some extreme environments. We've got cold, so it's getting a little chilly outside, right? We got to put our coats on, snow's here. I'm not happy about it, but it's here. But is it this cold? Okay, but is it this cold? No. So this is liquid nitrogen. Liquid nitrogen is the air around you cooled down from a gas to a liquid. And this happens at negative 321 degrees Fahrenheit, or almost negative 96 degrees Celsius. So really, really cold. You can see some really neat effects when you have stuff this cold. And so in here, I have some liquid nitrogen. I'll be safe, I'll put on the gloves. You gotta be safe, you gotta be safe. But one of the things that you can show, just as we have, I guess maybe I should keep one glove out so that I can operate. Oh, it's already on there, great. So I'm going to take a balloon. I'm gonna fill it with some air. Try that again. Thought about tying the balloon. All right. So we now have gaseous air, right? It's just gas inside of here. If I then place it inside of the liquid nitrogen, let me go ahead and put my safety gear back on. All right. And I grab my tongs because, you're not really supposed to stick your hand in there. And I push it down in there so it's actually in the liquid nitrogen. When I pull it out, you'll see it's taken up a lot less room. Oh, and wait, there's more. Come on. Here we go. And, oh no. One more. There we go. You'll see that as the air is chilled, it takes up a whole lot less room. But as it starts to warm up, that liquid becomes a gas again and fills the space that it has allowed. Another thing that you can show is more quickly how it can go from liquid to gas. And then we'll move on to more fun stuff. So take some liquid nitrogen. Again, it's a clear liquid. We pour it inside the tea kettle, and so all of you who make tea know that it starts to boil, or it starts to whistle when you've got steam, right? So I poured liquid in there. So it's instantly ready. All right, you guys ready for some tea? Okay. All right, so if I had more time, I'd do more stuff, but we don't. But I do want to show you an interesting material that we can utilize this cold environment to our advantage. That is superconductors. You see superconductors in MRI machines if you ever have to go to the doctor and get some imaging done. You can see it in bullet trains if you happen to go to Japan, and they may build one here in America one day, as well as at some of the largest scientific apparatus ever built, the LHC. This is one of the Atlas detectors at the Large Hadron Collider, which is where they're smashing particles together and seeing the fundamentals inside. So if you take these superconductors and you chill them down, superconductors are made of various materials. This one here is a yttrium, barium, copper oxide, so YbCO, and it's just a ceramic, and they put it all together, they push it into a puck, and then we chill it. And when you chill it, it has a neat advantage, oh, that's a magnet inside there, has an advantage of reducing the resistance and basically having no resistance, so current is able to travel without any loss or very, very minimal loss, which is why it's used in research and in medical procedures. But we just do something really neat. So this, once it's chilled, remembers the magnetic field that it lives in, which is from the Earth itself. And if I place a magnet above this, it actually will reside in this little well above the surface of the superconductor. And I got it on the first try. So this allows for essentially a frictionless bearing. Oop, but I drop it afterwards, look at that. A frictionless bearing, so it could spin with minimal loss, especially if we had no air in the room. So that is superconductor, so it's a very neat materials. If only we could find room temperature superconductors, we would change the world. Still haven't gotten there, though. And then the next thing, I forget, was, pools of Titan. So we had a talk done by John Monnier. He came, he does research on planetary science. And one of the things he wanted to show people was that in extreme environments, just as we chill air and it becomes a liquid, we can also do one better and chill natural gas, which is methane, and show that in extreme environments like the moon of Titan around Saturn on the far reaches of the solar system, that it is cold enough to actually have oceans of methane instead of water. And so this is supposed to be pre-chilled. I forgot to fill it, so I'm waiting for it to stop hissing. All right, now we're going to enter some gas. So what you're seeing above here is actually the natural gas coming out of the tube. This down here is just the liquid nitrogen forming over. But what I'm doing is I'm putting it down into a test tube full of, that's chilled with liquid nitrogen till I can finally get some liquid methane. And if I do that, let's see here. I'm going to break a rule and not put my hair back, but, you know, stay far away. All right. So we indeed can have liquid methane, and in a place like Titan, they have oceans and oceans of it. So hopefully nobody ever goes there and tries to start a fire. All right. Another extreme. We're already there, right? Space. So up in space, as was mentioned in previous lectures, nobody can hear you scream. And the main reason for that is there's no air to help propagate your sound out. And so we have to combat that anytime we leave Earth. And there's other research avenues where vacuums are used, and feel free to come and talk to professors afterwards to see what they may use it for. But we use vacuums for fun. And for physics, of course. And so Nick and Sean are currently setting up our cannon. On Sean's side, he's going to place a piece of freezer paper. This is going to seal the end, because one side of freezer paper is waxy, the other side is just paper, but it provides a nice seal. And on Nick's side, he's going to place a tiny ping pong ball on this side and then seal it with another piece of freezer paper. Once they have that set, we are going to evacuate or remove all of the air out of the white tube. And I will have you guys concentrate on your left side with this soda can. One thing that you might find about us demo labbers, we're not too fond of ping pong balls and soda cans. They end up getting sacrificed quite often, but it's all for science, right? And so once that is set, we're going to go ahead and begin evacuating the tube. Is all set? All right. So this takes some time, but we're going to pull out all of the air. And once you go, we're going to do a 3, 2, 1. Cover your ears. 3, 2, 1. Oh. Uh-oh. Something happened. Well, that's because sometimes demos fail. It's a little lackluster, right? But we have a few notable ones, and maybe if they can get it right, we might see it succeed at the end. But one of the recorded failures I have is from our very own David Gerdes, who did a talk on the physics of roller coasters, and he wanted to show, over here, how centripetal force works, or centripetal acceleration, excuse me. And so he filled a beaker with some liquid.
That will break into a million pieces if I screw this up. And so
it's just a beaker on a platform. And
oh no!
Fell off the platform. However, I invite you to go visit Carol after in the gallery and try it for yourself. See if you are more successful than David Gerdes. Another notable failure we had, but I do not have video of it, is when another professor from here, Professor Tim McKay, there we go, had used a demonstration known as the killer capacitor. This got its name because it unfortunately almost killed 2 professors, but we have since made safety an important aspect of all that we do, but we wanted to perform it for you successfully today. Yes. So we have, very similar to the cannon, we had that big gray box that we charged with a lot of energy. We're going to do the same thing, but we're going to put 3 of them together and do it more. So we're going to have about 10,500 volts, sorry, units are bad, volts stored into these capacitors. And so these big capacitors actually came from the old synchrotron on North Campus back in the 60s when we used to have a particle research being done up there. And so if you want to go ahead and get it started to charge, we're going to place a can halfway above and halfway below a set of 4 turns of a coil of wire. As we charge this up, we are going to store all of that energy into those capacitors. Just to give you an idea, those are for high voltage. This is the equivalent capacitor for low voltage. So tiny. Something like that, you want to have lots of space and storage available. Now, what's going to happen is once it's charged up, we're going to discharge it. We're going to release all the energy at once. It's going to travel through those coils of wire. It's going to produce a magnetic field, similar to what we saw earlier. And we're going to see it do something to the can that's inside. All right? All right. So this is going to be loud too. 3, 2, 1. Thank you. And so the neatest thing is it cut the can in half. And so you can ask me afterwards if you're curious as to why they look different, but for time's sake, we're not going to do that. But the main reason why this was so dangerous with all of that energy inside is you see it's in a box. It's pretty safe. Well, these screws used to be metal, and metal conducts electricity. And poor Tim was talking about it, and it discharged through his arm. And so thankfully it was only his arm and not through both of him, or all of him. He is here. So he is alive, Tim. So we're happy to have you here. And he even told me that he finished the lecture and still owns the shirt that he was wearing that day. All right, so really quickly to kind of wrap things up, we really want to talk about the legacy and future of our program. And so one of the legacies is our graduate student talk. And so back in 2014, we had a gracious donation from the Van Loo Family Endowment that specifically allocated money for graduate students to get practice presenting their research to the general public, to really just give them this platform. We've had 10 talks in the last 11 years. We only missed COVID because it was near the end of the semester and it shut down. We've had a total of 28 speakers, and I had to look them up, see where they are now. I could only not find 4 of them based on the quick search I did. Most of this came from LinkedIn, so the current students and recent grads probably just didn't update their thing yet. But this is a nice little breakdown. We see that the vast majority of them actually went into industry and government. We've got a fair bit, about a quarter of them, or a fifth of them in academia still. And hopefully these recent grads and current students will get to do some great stuff in the future. Another legacy we have is our extravaganza. And so the students who were here last year got to participate in a presentation where we launched the idea of the STEM-mobile. The STEM-mobile is a program that we're trying to bring STEM outreach to local schools around us, anywhere we can reach in a van. And what made this event so great was it was actually our largest number of participants. We had 23 people involved in the actual presentation. And it came from multiple departments around the university. And the biggest thing that came out of it was really to spark the love of public engagement and science communication among this group. So please keep your eyes out, more to come. But really, we have a legacy of very diverse speakers, whether they come from on campus or abroad. We have a history of science communication. It's very important to us. And these are the things we would like for the future. We want to continue to bring scientific leaders. We want to develop partnerships with schools. We used to have schools come and visit us on Saturday Physics, but it was an extra credit thing, and unfortunately that is hard to do these days, and so we would love to be able to develop an additional outreach. We would also really like to make this a self-sustaining program. Currently, we rely on funding from the department and other sources that aren't secure, and so this would be one thing that we would like to do, and hopefully we will. We would love to bring SMP swag, and although Tim likes donuts, I want the bagels back. Oh, sorry. Just in case, I need an exclamation point. And in our rich history, particularly for the young ones, we hope that we could feature you here in the future. And so, just to wrap it up, we want to give some thank yous. We've got the faculty, the demo lab staff over the years. We've got Michigan Media and all of their help. So thank you, ladies, and everyone else, and Carl in the back, and everybody else who was here before me. And then, of course, the special thank you. We couldn't have done this without Carol.
We need to bring Carol down here
Yes.
to join us just for a moment.
Behind the scenes.
Oh, yeah. Well, Carol, this is your moment in front of the lights.
Whoa.
And, and thanks for coming down. All right, this is what makes it all happen. So, Carol, you've been a wonderful partner, and we've worked together for so long, for so well, and with everybody else. Actually, I don't know exactly how many years it's a team effort led by Carol. So also, everybody, Carol's birthday's coming up.
Monday.
On Monday. So we have a card for you, and we wanted to really thank you for everything you've done for Saturday Morning Physics.
Thanks.
Can you hear me? Oh, yeah. And also, we'll let Carol speak, but we have to give her a microphone.
She has a microphone.
You have a microphone?
She's
Okay,
just
go
being
ahead,
shy.
I'm in shock. I'm behind the scenes, and I love people. I love communicating science, and I love showing science through this wonderful team. And I just appreciate every one of you for coming, showing up here, and eating our donuts and hopefully bagels in the future. And if you could please find it in your hearts to donate a little bit of funding to keep this program alive, it would be great. Thank you.
Thanks, Carol.
So shall we end with a bang done the right way? Shall we end with a bang done the right way?
Yes.
Yes? Carol, do you want to do it? You just got to, yes, yes.
Tell me what to do.
Place your flowers somewhere safe.
Yeah, put your flowers up. Am I safe?
Place it not down range.
All right, so let's try number 2, see if we can get it right the second time around. There. Wait for it. Woo! It was still leaking, yes. All right. And so the poor can took the impact of the ping pong ball. All right, so again, thank you all. If you would, we may have some questions, but we also have demonstrations outside as you are leaving, so please feel free to partake as you are exiting. So thank you. Thank you. Thank you.